சார் வணக்கம்ங்க. பிரபாகருங்க. சார் வணக்கம்.
வணக்கம். Is it
yeah, it's me, பிரபாகரன்.
பிரபாகரன்.
ஆமாங்க ஆமாங்க. நல்லா இருக்கீங்களா? எங்க வீட்ல நல்லா இருக்காங்களா?
எல்லாம் நல்லா இருக்காங்க. Thank you.
சரி.
இல்ல சௌரியம் தானே?
நல்லா இருக்கேங்க நல்லா இருக்கேன்.
Happy New Year to all.
Happy New Yearங்க. ஆமாங்க.
Thank you.
சரி.
என்னோட வாய்ஸ் கிளியரா இருக்குங்களா?
கிளியரா இருக்குங்க. கிளியரா இருக்குங்க.
ஓகே. சோ இப்போ நாம எப்ப ஸ்டார்ட் பண்றோம்?
ஒரு 5 நிமிஷம்.
ஓகே, நோ ப்ராப்ளம்.
சரிங்க சரிங்க. Thank you.
Thank you.
Professor, shall we start?
Yes, I'm ready. We can start, please.
Good afternoon, friends. It gives me an immense pleasure in inviting our Honorable Professor Dr. Prabhusankar sir for this virtual conference. Indeed, his busy schedule, he accepted our invitation, and he was the one actually who first accepted his. He has given his concern for the first. Provided, as far as his credentials are concerned, sir, he did his master's at Madras University and PhD at IIT Mumbai. Then he moved to his postdoctoral research fellowship to France in 2004, EGIDE postdoc. Then he was working as CNRS postdoctoral scientist at University of Rennes from 2006 and 2007. Then 2007 to 10, he was being awarded a prestigious fellowship, AVH fellowship from government of Germany, and he was at Germany. Then 2010, he took up a position as assistant professor of chemistry at IIT Hyderabad. Then 2015, he elevated to associate professorship. During his tenure, he was serving as dean for students affairs in 2018, and subsequently he was the chair for admissions hostel. In 2019, he promoted to full professor, and he is the capacity as professor. And as per as his credentials, the awards, sir has been awarded DUO as a post professorship in 2020, Best Teacher Award, and AVH Fellowship. As per as his credential, he has published more than 100 research articles in highly reputed journals. JAX, Anglo-Andy, Chemcom, Dalton Transaction, Inorganic Chemistry, Organometallics, Catalysis Today, so on. Actually, it needs a lot more time to say about professor, because when I was looking his website, it seems plenty to discuss about professor, but due to the shortage of time, and I don't want to take much time, and I am humbly giving the session to professor to share his expertise with our participant. Definitely, I do hope our participants will get more information from professor's talk. I hand over the session to professor. Once again, I am welcoming you, professor, on behalf of chemistry department and recent trends in chemistry 2021. Thank you, professor.
Thank you very much. So, very good afternoon, one and all. This is Prabhu from IIT Hyderabad. I'm working as a faculty here in Department of Chemistry. Professor Prabhakaran, I'm very kind of you for introducing my professional career. Thank you very much, and I am also thankful to the RTC 2021 committee members for inviting me to share our ongoing research work at IIT Hyderabad. So today I'm going to discuss about part of my ongoing research work at IIT Hyderabad on NHC late transition metal, N-heterocyclic carbene late transition metals in medicinal chemistry, catalysis, and light emitting applications. Hope my voice is clear to you. In case if you have problem, do let me know. I'm actually tracking the YouTube chat box also. In case of any issue, do post. I'll immediately respond to it. That's point number one. Point number two, if possible, try to mute yourself and use a chat box in case if you wanted to post your questions. All right. Thanks a lot. Let me formally begin my talk by thanking Professor T. Suresh and Professor R. Prabhakaran, Department of Chemistry-Bharathiar University, India, for inviting me to share our ongoing research work in RTC 2021. Thank you very much, Professor Prabhakaran, particularly. And to Suresh. Yeah, thank you very much. I'm looking forward to meet you all in your university. So your university is one of the world's university. I remember way back when I completed my undergraduation, I traveled all the way to your university and knocked your department door and inquired your head of the department whether the department is ready to accept the MSc application or not. Your head of the department, Professor Nadarajan, if I'm right, at that time got really shocked. He said, look, the exam is not over yet, because at that time I was, my college was associated with the Madras University. So he said the exam is not over yet, so please do come after a month so that the call will be out and you can apply. But however, I couldn't really make it at that time. Therefore, I moved all the way to Chennai to pursue my MSc program. Anyhow, that's all whole story. And the work what I'm going to share today is not mine. Unfortunately, it's all my students' hard work, and my students are sitting over here. So I thank sincerely all my students for their hard work, dedication in the laboratory. Also, I thank my co-workers, colleagues, Professor Osamu from Rishmakan University, Japan, and Professor Basant K. Patel from Biotechnology Department, IIT Hyderabad, for biostudies and material-related studies. Of course, I must always thankful to the funding agencies for the too generous financial support to my laboratory to carry out my research at IIT Hyderabad. So what we do at IIT Hyderabad, we work on 3 different themes. One is catalysis, second is medicinal chemistry, third is luminescent material. What I'm going to do today, and I'm going to just give only one example per application and then conclude my talk. So then what we use and how do we achieve these targets? We use the kind of molecule called N-heterocyclic carbene. Okay, we attach N-heterocyclic carbene. We tag N-heterocyclic carbene with the N-heterocyclic aromatic ring system called acridine. Okay, acridine. This is called acridine. 3-membered. The 3 fused 6-membered heterocyclic compound called acridine. Only one nitrogen is present in the middle ring. Right. So, with this molecule, we have demonstrated the medicinal chemistry application as well as catalysis as well as luminescent properties. Right. Before I proceed, I would like to certainly introduce about my institute. You know very well where the IIT Hyderabad is located. It's in the middle of India almost, right? We got now 23 IITs across our country. IIT Hyderabad is one among, is known as second generation IIT, established in 2009, 2008 and 9 with just 43 faculties, 180 students. Okay, so I in fact myself joined at the same time to build the institute. We started our career with only 9 R&D projects across the institute, by the way. And in 2019-20 celebrated the 10th anniversary of our IIT. And so current faculty strength is 240, student strength is 3,000. And we have received so far about 850 plus R&D projects, published about 3,020 papers, 81 patents, and the current PhD strength is about 900. Okay, so therefore this accounts roughly about 4 students per faculty, right? If you look at our department, chemistry department, established after I joined in IIT Hyderabad with 6 faculties, 14 students. So we had at that time only 7 MSc students, master students. You can see them here. And current department strength is 16 faculties, 180 students, in which 100 are master students and about 80 are PhD scholars. So we got roughly about 1:1 UG-PG ratio in our department. So when I joined, we started with a very humble background. We had a very limited facilities. I have shown here my old laboratory where I was actually working, and the work what I'm presenting today is actually from the same lab. So, when I joined, we had a very limited facility, and we were given a space in the tanker manufacturing site. It's called Ordnance Factory, where I was very lucky to get one cycle shed and established my laboratory. This was the cycle shed, and of course, all these crotons, whatever you see in front of laboratories, are our own students gardening. and so then bought a syntax tank and no drainage and so on, established a laboratory and worked there for about 8 years. And then in 2019, we were lucky to get 3 buildings. What you see here are located in our permanent IIT Hyderabad campus. So where we got about 13 departments. Okay, and so you know about IIT system, the UG course is very intensive course, and so therefore we need to have enough classrooms to run out the UG program. Now, just want to show you some beautiful pictures of our campus. Okay, this is the actual picture of my campus, and what you see here are known as the iconic buildings of IIT Hyderabad, are known as hostels. Hostels are centralized AC hostels. So each student gets an individual room. Okay, it's like a hotel, and so the temperature of the room would be always 25 degrees centigrade throughout a year. And what you see here in the left corner side is called a dining hall. We got a one single centralized AC dining hall for everyone, where about 900 students can take a lunch or dinner or breakfast in a given point of time. It's a quite big hall, okay, AC hall. So the second important point about IIT Hyderabad is about funding opportunities from foreign country. When our IIT is the first IIT in India to attract or to have a very strong foreign collaboration to attract a huge amount of financial support from Japan. And we received roughly about 1,450 crores of money to establish our campus. So Japan is going to therefore support in two ways: academic support to exchange the students as well as faculties, B, infrastructure support to build our campus. So with their help, we started our construction. The construction is going on now to build 25 new buildings. Okay, 25 new buildings, and with this 25 new buildings and 10 new hostels, we would be able to accommodate roughly about 5,000 extra students on our campus, and we can add additional 20 more departments to our institute, and campus size is 576 acres. Almost we will be completing the construction of our entire campus by 2025 if all goes well. Okay, our actual plan is to accommodate roughly about 20,000 students. By the way, if you compare the age of our institute is just 10 years, like a baby of Bharathiar University. Bharathiar University is more than 25 years university and well established university, and I'm very glad and honored to deliver my talk in Bharathiar University. Therefore, now coming back to my department, our chemistry department is going to come up in this particular plan. We're supposed to get in 2021. Okay, and if it comes, our chemistry department would look like this. It will be a kind of elegant department, iconic department. Unfortunately, due to COVID-19 issues, what went wrong? We have stopped all the constructions. Okay, at some point, and then we restarted now. So therefore, this is actually what you see here in the front is the Department of Chemistry building, upcoming building. We supposed to have 7 floors, but as you can see, it is stopped at the second stage, and eventually will come up. I mean, basically, I have not added the last figure. Hopefully, it will come up within 2025. And what you see here, the tiny, tall, white tower is the faculty housing. Okay, and I stay in this building. Okay, right corner tower, which is 17 floors tower, and where I stay. So from here, I can certainly see my department. You know about IIT; it's a residential campus. So not only that, the COVID has also got a tremendous impact on academic system too. We have stopped the mobility among institutes, academic institutes, and funding is questionable. Research is questionable now because of the restricted rules and regulations. And believe me, this is not my own message. It's a message from Nature, and this particular article was published on 20th May 2020. Okay, the message, this particular article clearly says that US and UK lost terribly because of the COVID lockdown followed by uh, measures. So the US, for example, alone lost roughly about 84% of their academic income, while UK lost roughly about 16% of their academic income. The reason behind is we send roughly about millions of students to US and UK for their higher studies. So this year, unfortunately, we couldn't send not even a single student because of the travel restrictions and so on. Same time, if you look at the number of publications, research output also got severely affected by COVID-19. See, what went wrong today is following, and male faculties are performing very well compared to female, or rather male faculties are doing the same job, but unfortunately the lady faculties are suffering to cope up the current situation. As a result, the number of papers published by lady faculties keep dropping while male faculties keep increasing. Rather, it stays at a constant level. Okay. Now, therefore, the regular mode of interaction. See, for example, we supposed to meet in person and deliver. I supposed to deliver a talk in person, but which is not happening here. So, and this is questionable today, and therefore we heavily rely on one of the technique which I have listed out in the right side, right? So we have no other choice other than relying on these invisible techniques to communicate each other by maintaining a social distancing. So therefore, you are sitting somewhere, I am sitting somewhere. So however, we try our level best to communicate each other effectively. Now the question comes, what else COVID can do? It can definitely, the article again, the BBC clearly says that it can actually, severely affect the health of human being. Therefore, people do worry a lot about the overweight, obesity, and so on, because the no physical activities and their physical activities have gone down drastically, right? Same time, I just wanted to highlight this most important message that was published by Harvard University on 28th April 2020. That is actually the early stage of lockdown. So the Harvard University did an extensive research to understand the relationship between COVID-19 versus the brain activities or immune response systems. So they concluded that COVID-19 can certainly affect the memory of human being. Okay, and this particular disease is known as Alzheimer disease or dementias or Parkinson disease. Okay, Parkinson disease. So memory loss disease. So therefore, cut short, in a nutshell, I can tell you that COVID-19 can certainly create a complication to memory loss patient. The memory loss disease is known as Alzheimer disease. Okay, right. So why this happens? This is all because of social distancing. Okay, social distancing. Now the question comes, so in which way I am contributing to this particular research? It's a part of our ongoing research. As I said in the beginning, we use acridine based N-nitrocyclic compound to understand or to identify the suitable drug for Alzheimer related disease. So I'm going to give one such example in the following slide and then move on to another part of my talk. Now the question comes, what is acridine? Is it a new molecule? Why are you talking about this particular molecule? Acridine is known in the literature for more than 125 years. Okay, it's a too old chemistry, no doubt about it. Okay, no doubt about it. It's too old chemistry, and believe me, this particular molecule can be used as a drug. This was discovered by Professor Paul Ehrlich, German professor, way back in 1912. So he identified this drug and tagged it as acriflavine. The first acridine-based drug, name of the first acridine-based drug is known as acriflavine. Believe me, this particular drug is even today surviving in the market. Then you can understand the benefit of this drug. So you can also find several textbooks on this particular drug. For example, the textbook title itself starts like this: biomedical applications of acridine, and so on. This Professor Paul Ehrlich also mobilized for discovering many other drugs. That's all different story. The point which I would like to highlight here is following. Believe me, after 100 years, okay, or more than 100 years later, Professor Mark, okay, from UK wrote a book on acridine. In 2001, he wrote this book, a review on acridine, a neglected antibacterial chromophore. 6 years later, Professor Pliffet from University of Paris, France, wrote this particular review on acridine derivatives and anti-cancer properties. Okay, double dot, where are we now? He asked a question, where are we now? So therefore, this particular molecule has a tremendous commercial use potential. So therefore, by keeping this in mind, what we did is following. So, and we have introduced a functional group to 4th and 5th portion of acridine group. So that functional group is known as imidazole. Okay, 5-membered heterocyclic ring system introduced to this. It can happen in one single step. It's not a complicated story here at all. One can generate this particular molecule in 100% pure form in a multi-gram scale. Later, what we did, we introduced other substituent at N position. Okay, this substituent is essential in case if you wanted to make the drug as a water soluble drug. Okay, therefore this is called acridine imidazole. When I introduce the substituent at nth position, it generates a salt. This is called acridine imidazolium salt. Acridine imidazolium salt. This I call it as a drug. So we used this as a drug and investigated the Alzheimer property. Okay, and now I call this drug also as a ligand. So why? The reason behind is, if you use a base, you can knock off the CH proton here. Okay, there is a CH proton. I can knock off the CH proton and generate carbon with the 2 lone pair electrons. Okay, carbon with the lone pair electrons. Right, this is called carbene, N-heterocyclic carbene. Now you got a carbon, nitrogen, carbon donor chelating ligand. Beautiful CNC type of chelating ligand is now available. I can use this as a ligand and can use it as a catalyst support, or I can use it as a material support to eliminate a particular light. So therefore, I'm going to give one example for Alzheimer's disease using this molecule, and one example for catalysis using this ligand, and one example for luminescent material using this ligand, and then conclude my talk. Okay, now let me discuss about Alzheimer's disease. You need to know what is this disease and how this happens, and what is so important about why one should worry about Alzheimer's disease at all. Now, as I said, the acridine benzimidazolium salt can be used as a drug, and which we have used it as a drug for this disease. Before that, I should also give you some background information about Alzheimer's disease. It's known as memory loss disease. It is also known as the second most dangerous disease in the world, okay, after cancer. Right. The image itself is self-explanatory. When patient develops the Alzheimer's disease, the life of brain goes, and you see, as you can see in this last picture, and the part of brain is missing here. right? So therefore, the World Health Organization has allotted the world with the following message. It says, in every 3 seconds, we produce one Alzheimer patient. That is really bad. I mean, this particular fact sheet is not from my own databases, it's from World Health Organization. You can even visit the World Health Organization, you will get the same message. The World Health Organization says in every 3 to 4 seconds, we come across at least one Alzheimer patient. So every year we add roughly about 7.7 million new cases. That's very bad. And worldwide we got roughly about 46.8 million Alzheimer patients. So by 2030, in principle, this will become double. We will hit the figure called 74.7 million. This will become a triple in 2050, and we're going to have roughly about 131.5 millions of Alzheimer patients. The most shocking news is the following. Unfortunately, as you can see in this pie chart, the Alzheimer patients are much higher in Asian countries rather than developed countries like Europe, Africa, or North America or Latin America. Now the question comes, how it is related to Asia? God knows. I mean, there's no clear study on this particular aspect. There's no reason why Asian should, in principle, have more Alzheimer patients. Now, if you look at it, therefore, the World Health Organization has encouraged everyone to work on this particular disease and invested a lot. Okay, so in 2015, the World Health Organization has invested roughly about 818 billion US dollar. 818 billion US dollar. In 2018, we invested roughly about 1 trillion US dollar. This would become 2 trillion by 2030. This is a lot, by the way. Now, for your understanding, if you compare this particular investment versus the market value of Google market value is only 742 billion US dollar, while Google value is roughly about 368 billion. Okay, we are investing much higher than what one can think of to understand this particular disease. Now the question comes, why? What is wrong with this disease, and how it is different from other diseases? So therefore, to create awareness, the World Alzheimer Society has tagged 21st September as a World Alzheimer month, right? September itself is known as World Alzheimer month, and 21st September is known as World Alzheimer Day, right? Question comes, what causes the Alzheimer disease? The answer is very simple, okay? And so this particular video, I've adopted it from Nature magazine. So this can give you kind of information about Alzheimer disease. So what causes Alzheimer? Why, how the Alzheimer can happen to patient, and what is happening in the brain? What is brain? What is happening in the brain? What causes the Alzheimer disease? You will have answer to all these questions in this particular short video. Okay, and hopefully you will get a voice. If not, then I will see my level best to also help you out to get a clear voice for this particular video. So in case if no voice, I suggest you to use a YouTube, the chat box, and say no voice. I am just keep monitoring the chat box, and I can immediately do something to get a voice for this particular video. Okay.
over a century ago, a German doctor called Alois Alzheimer spotted anomalies in brain sections from a patient with dementia. Ever since, people have been studying the strange plaques and tangles that he saw, in the hope that we could one day understand and cure what is now known as Alzheimer's disease. Plaques are insoluble deposits of a peptide called amyloid beta, or A-beta. They're formed when a protein called amyloid precursor protein is sequentially cleaved by two enzymes, beta and gamma secretases. Other molecules are generated by this cleavage and may play a role in the disease, but A-beta is the main culprit. A-beta tends to misfold and become sticky, eventually clumping together to form soluble oligomers. Some of these aggregate into large insoluble fibrils that deposit in the brain as plaques. The oligomers come in several forms or species. We don't know exactly which species is toxic, but research shows that they weaken communication and plasticity at synapses. This could be what stops the brain from forming or retrieving memories. Neurons aren't the only cells affected in Alzheimer's disease. Astrocytes and microglia also play a role. Microglia are immune cells that clear out waste and prune synapses during development. Microglia take up A-beta, but they also get activated by it, triggering the release of inflammatory cytokines that can damage neurons. The microglia also start to remove synapses by phagocytosis. As synapses start to malfunction and neurons die, abnormal patterns of activity emerge, and eventually, the brain can't process and store information properly. Another key feature of Alzheimer's disease is neurodegeneration. Neuronal death and damage is triggered by A-beta, but some of A-beta's effects seem to be mediated by another protein seen in the brains of patients, tau, a component of tangles. In a healthy neuron, molecules are carried along the axon on a series of tracks, made of microtubules and stabilized by tau. But in Alzheimer's disease, tau is modified, causing it to dissociate from the microtubules, adopt an abnormal shape, and move from the axon to the cell body. Like A-beta, tau comes in a variety of forms, and we don't know which ones contribute to the disease. And like A-beta, these forms either remain soluble or stick together and deposit as the tangles that Dr. Alzheimer saw. Eventually, these processes kill the neuron. Another problem seen in animal models is that misfolded tau proteins can spread across synapses into healthy neurons. There, they make healthy tau proteins start to misfold as well, spreading pathology across the brain. The pattern of spreading through the different brain regions matches the changing symptoms from early to late stages of Alzheimer's disease. This pattern also reflects how certain neurons are more vulnerable than others to dying. Despite these advances in our understanding of Alzheimer's disease, no cure exists. While drugs are being developed to target amyloid beta or tau, it's unclear whether they will eventually be successful in treating the disease. There's only one certainty. Continued support for basic and clinical research will enable us one day to diagnose and treat this devastating condition.
Right. So I hope my video is clear. In case, if not clear, you can unmute and say if you have some concern about this particular video. If not, I'll just summarize about this particular message. The message is following. The video ends with the following quote. Point number 1, the Alzheimer can occur. Alzheimer disease can be generated by two reasons. One is beta amyloid plaque formation, Reason number 2 could be tau protein. Okay, the tau protein, beta amyloid, only 2 are responsible for producing Alzheimer's disease. Beta amyloid can form a plague. The beta amyloid can misfold and form a beta sheet. Beta sheet can become a plague. Okay, or tau protein can form a triangular. Right. So in both the process, what happens to brain is following. The neural network shrinks. Okay, basically they behave like a wire. The wire length decreases. As a result, the patient would face a trouble to communicate. He will not be able to communicate efficiently. Okay, and then the last take-home message of this particular video is, I hope, it says, the video says, hope one day we will have medicine for this particular disease. This is absolutely true. Today, there is no medicine for Alzheimer's disease. So the research is in the basic level, and all are working towards understanding this particular disease and generating a proper medicine for this particular disease. So therefore, I got a summary of the videos here. The Alzheimer's disease was discovered by Professor Alzheimer, okay, German psychologist and neuropathologist. So he invented this particular disease from patient called Auguste Deter in way back in 1907. Okay, at that time patient age was 57. So he discovered, he's actually a doctor, a professor who discovered this disease and tagged this disease on his name as Alzheimer. Okay, so what Alzheimer does? Because of Alzheimer, the brain mass can decrease. It's a healthy brain, and what you see here on the right side is a Alzheimer brain. So the brain shrinks, the brain mass decreases. Why? This can be because of amyloid plaque formation. Okay, amyloid plaque can form because of beta amyloid, or neurofibrillary tangle formation. Neurofibrillary tangle formation, like this you can see here. You see all this tangle, neurofibrillary tangle formation. The neurofibrillary tangles can form from tau protein. Okay, the tau protein is responsible for this. It is one of the most challenging disease for scientists today, and very difficult to isolate the drug. The success rate is 1 out of several thousand. Believe me, this is the fact. Okay. Now, how to prevent the Alzheimer's disease? So let's look at one mechanism. So the Alzheimer's disease happens because of beta amyloid plaque formation. Beta amyloid plaque forms because of beta amyloid sheet formation. Beta amyloid sheet forms because of beta amyloid protein. Beta amyloid protein forms because of TDP43-YFP cell. Okay, what is this? Transactive responsive DNA binding protein 43 kilodalton. It's a very small protein. Okay, yellow fluorescent protein. Okay, yellow fluorescent protein. So therefore, the origin for Alzheimer's disease is TDP43-2C. That's it. Now, if drug can stop at this stage, step 1, I mean, then no issue at all. If not, at least the drug should be active at the end of the whole cycle. It should not allow beta amyloid sheet or beta amyloid plaque to progress further and form, generate the disease. So therefore, the good drug should work either in step 1 or at least, at least it should be active at the end of the whole cycle. Now, let us look at what is TDP43. It has got 43 amino acids. It shows a smooth rod-like structure. Diameter is about 3.1 plus or minus 0.2 nanometer. Length is about 60 to 220 nanometer. Therefore, to summarize here, TDP43 is responsible for forming plaque. Plaque is the one which causes Alzheimer disease. Keeping this in mind, what we did, synthesized a new drug molecule in our laboratory. What we did, it's a couple of step synthesis, and no side for product at all. One can get 100% pure pharma product in crystalline stage. We can crystallize these molecules, and we have also investigated the crystal structure of these molecules. Stable, one can also isolate these molecules in a multi-gram scale. You can also exchange the anion with a suitable anion, bio-friendly anion, okay, in a single step. Okay, this is acridine methyl bromide coupled with imidazole substituted N-substituted imidazole to generate a drug. It's a one-step synthesis, multi-gram scale synthesis, and isolated in 100% pure form, no side product at all, crystallized, and I also understood the crystal structure of these molecules. So we have produced 5 different types of derivative molecule drugs. Drug 1 consists of acridine, imidazole, ester group at the end, bromine is anion. That I call it as acridine imidazole 1. That is AIM-1 drug. AIM-2 consists of isopropyl substituent PF6 anionic group, and AIM-3 consists of the same. Instead of PF6, here you got a BF4. Then AIM-4 it's basically a carboxylic acid. We hydrolyzed this product and produced a carboxylic acid derivative of salt. That is, I call it as AIM-4. I repeat again, AIM-1, AIM-4 difference is, this is ester, this is carboxylic acid. Then you got another final drug is called AIM-5, which is nothing but a derivative of AIM-2, AIM-3, only the anion is different. So to summarize or to explain in a short way, AIM-1, AIM-4 are of nearly same family because the N substituent is ester here, and here you got a carboxylic acid. AIM-2, 3, 5 got isopropyl substituent, only anions are different. Okay, nice. And what we did, and we have studied the inhibition property of this particular these drugs with the TDP-43 protein. So the experiment goes like this. So we need to use a reporter dye called thioflavin along with the TDP-43. Okay, we mixed the TDP-43 thioflavin titrated with different drugs of known concentration. In case if drug shows inhibition property, in principle, you will see the changes in the emission property of thioflavin, okay, THT. So if there is I repeat again, if there is a contact between a drug and this protein, okay, the responsor dye will tell you that there is a strong interaction between a drug and protein. If no interaction, you will not see any changes in the emission property. So therefore what we did, we just did a dummy run only with the protein and THT, which is here, the black line represents a dummy run, and then introduced this equal concentration of AIM-1, 2, 3, 4, 5. The outcome is following. You see here, certainly all are active. Out of all, please pay attention to the last line, which is caused by AIM-4, okay, where you got a carboxylic acid terminal, bromine as an anion. Seems to be extremely active. It has quenched drastically compared to any other drug. Therefore it has quenched about 76%. Therefore, we increased the concentration of, we picked AIM-4 as a suitable drug and further increased the concentration of AIM-4 towards the protein. As you can see here, it strongly interacts with the protein at one stage, it flattens almost. So therefore, and concentration, if you look at it, which is the concentration is absolutely very less. So therefore, this particular AIM-4 is seems to be the active drug. Okay, the carboxylic acid is very much essential to dissolve this drug in a biofluid. It is also bio-friendly, right, biocompatible, and imidazole group, acridine, all are very much essential for the drug activities, which I will not be discussing in detail, but we have done enough studies to prove the importance of all the functional groups. You can also track this particular activity using AFM technique. What you see here, the left side is without drug and the right side is with the drug. Very simple. Without drug, the TDP-43 accumulates and forms a nice fiber, okay, protein fiber. So you can see here, it's quite long or gently bent fibers are formed without drug. With the drug, it's completely a disaster, and there is no such a long shape protein exists in the medium, which means it disintegrates the protein, never allows the proteins to grow or never allow proteins to form a fiber or beta sheet or play. Okay, so what it did, what it has done, basically what you see here is a granular spherical oligomeric structures with an average size of 5 to 10 nanometer. So it therefore take home message here is it prevents the beta amyloid accumulation. It never allows a beta amyloid to form a beta sheet or play. So therefore, this particular drug stops here itself in the first stage 1 itself, which is extremely important, very, very important activity of a drug. So any drug, if you think, or that can be even cancer drug, that can be even Alzheimer drug, should be extremely active in the early stage itself. It should not act at the end of the whole cycle, which is very dangerous, right? Now, however, what we did, we wanted to also see how this particular drug is responsive to the matured patients. Let's say patient has crossed the early stage and is in the last stage, where he has already developed enough quantities of beta amyloid sheet, insoluble protein sheet. Now, can my drug act at this stage? The answer is yes. How? We have proved it using circular dichroism. And so the black line, for example, represents TDP-43 aggregates, right? Beta sheet aggregate, and the green line represents monomer, and blue line represents TDP-43 with the drug. Okay. Now, I mean, I will not go in detail to all the plots, but I'll just summarize and tell you that certainly the drug is active at this stage also. It decreases the beta amyloid concentration in the biosystem. How much it decreases? It decreases roughly about 20%, which is actually in principle lot compared to any other molecule which shows this particular activity. So to summarize the drug activity, I can clearly tell you that AIM4, the one which has got a carboxylic acid functional group, is highly active towards TDP-43 as well as the mature stage, that I call it as a beta sheet formation stage, and prevents even the beta amyloid sheet aggregation also. Okay. Next important point, highly selective. Third important point is not toxic at all to cell. We have also investigated the cell toxic effect. It is absolutely cell-friendly, no issue at all, right? And we have also investigated the mechanism, okay, and the drug metabolism. You call it as a drug metabolism, how it interacts with the protein and so on and so forth also. So therefore, this particular work, when we published, this was in fact highlighted by Alzheimer Forum. It was listed in their important reference list. And eventually, when we investigated further and published the metabolism, this picked up media attention also. This was on, if I'm right, you can see here, this was on February 4th, okay? On February 4th, 2020, this particular work was actually attracted by pharma companies as well as medias of our country. And in almost all the magazines as well as in the newspaper, this was highlighted. At the same time, we were surprised that this was also appreciated by the Honorable Educational Minister Dr. Ramesh Pokhriyal ji, and tweeted about our work in his personal Twitter page, and said the incredible team of researchers from IIT Hyderabad have found a new molecule that could help in finding cure of ALS related diseases. And so you can see in the bottom also, we surprised, to our surprise, even the Honorable Prime Minister Narendra Modi ji as well retweeted and appreciated. So, in fact, this particular work also motivated us, particularly to our group, to work on this molecule further, see the potential of this particular molecule. What we did in the second case, we converted this medicine as a material. How? And we used this as a catalyst support. As I said, this particular drug consists of acetic CH proton. I can use a base and generate a CNC type of chelating ligand. And I used this chelating ligand to support the palladium metal, and used this particular palladium CNC type of catalyst to reduce or to partially reduce the alkyne molecule. Okay, alkyne, semi-reduction of alkyne. What is this is absolutely not so great, but what is important here is about the selective reduction of alkyne. Okay, so one should not produce the impurities when we reduce the alkyne. This is important for certain high-end applications. So for example, when we for example, the high quality medicinal grade or semiconductor grade PVCs or related materials should be of very pure form, should not have the contamination. So that is possible only with the help of high pure ene. Okay, high pure ene. So particularly when we reduce alkyne in the presence of palladium 1 or palladium 2 or 0, in the presence of hydrogen, you end up in generating Z-ene, E-ene, ane, completely reduced, semi-reduced, two different products, okay, in cis form and trans form. So these are all impurities, and all these impurities can terribly spoil the quality of material. So only if you produce a material with the help of ultra pure product, then you generate the medicinal quality or semiconductor quality appliance for commercial purpose. This particular work was initially investigated by Professor Elsevier from University of Amsterdam. Okay, so he used a palladium N-nitrocyclic carbene supported palladium 0 catalyst with the help of in the presence of hydrogen gas in PHF to reduce alkyne into alkene as well as fully reduced. So unfortunately, he couldn't really isolate a single compound. He was not able to achieve the target, and however he received one product as a major product and additional 2 products as minor products. Look at here, he used hydrogen gas as a reducing agent, which is actually not a friendly gas when you're talking about industrial scale reactions. So the same group reinvestigated this particular reduction process and used only 1% of palladium 2 carbene catalyst. Look at the hydrogen sources, replaced the hydrogen source, hydrogen gas, by formic acid and triethylamine. So he used acid and base as a source to produce to supply enough hydrogen to this particular reduction process. However, he was not able to cut down the impurities. Okay, and then therefore he worked further, and also other groups as well, and concluded the following point. So if you look at the history of this reduction process, way back in 2005 it was started and produced all the products, one as only major product with the help of hydrogen gas. Later on, palladium 02, palladium and etc. were used in the presence of formic acid and triethylamine to cut down for some extent one of the impurity. Ultimately, they achieved to isolate more Zatin, less Ein, but no Ain. Okay, that is a completely reduced product. However, this is not sufficient. So, therefore, the question comes: is it possible to make only Zatin? Okay, or how to prevent the corrosive reagents such as triethylamine, formic acid, or not friendly chemicals for industrial applications? So we can't use them. Keeping this in mind, what we did, as I said, we picked one of the drug molecule as a precursor and treated directly with the palladium acetate in DMSO 4 hours under vacuum neat reaction to isolate the palladium carbene compound and crystallize this particular catalyst, and understood that the no direct interaction between palladium and acridine nitrogen. However, the two carbenes are coordinating to palladium. Palladium is in a +2 oxidation state attached with the 2 carbene neutral donor ligand and the 2 bromide ions, right? Square planar geometrical form. So it's a first acridine NSC supported, NSC attached with acridine supported complex, right? But I stress once again, no direct bond between acridine and palladium. Now I'll come back and explain the relationship between acridine and palladium after some time. Now, therefore, we used this as a catalyst, okay, and to reduce alkyne into alkene, and in the presence of triethylsilane and methanol. Note here, we have changed the hydrogen sources. Now we did not use a formic acid and triethylamine. Here we used triethylsilane and methanol. In DCM, 2 hours 30 minutes performed this particular experiment, used 3 mole% catalyst to do this particular process. Now, for our understanding, okay, to convince you, what we did, we picked we prepared a similar catalyst but without acridine. You got a simple CH2 group in the backbone. Okay, so it is an identical molecule. The only difference is here you got acridine, here no acridine. You got a simple ethyl group. That's all. Good, very good. What we did after that, so we picked 15 different alkynes with electron donating or withdrawing and so on and so forth, and did the reduction process. And we used a catalyst, the black box catalyst, acridine and palladium catalyst, as well as the red box catalyst. So the line, the black line, therefore represents the product isolated, okay, product isolated using this catalyst. The red line represents the product isolated using this catalyst, and this is actually the yield of the major product. As you can see here, in most of the cases, okay, in the most of the cases, black line is dominating, right? Means this catalyst seems to be more active than this, right? Right, for at least a few cases. Now, how about a minor product? I would like to draw your attention to these, particular plot. It's a very important plot. See, please pay attention here and look at the flat lines. Okay, again, the black line represents the minor yield of minor product isolated using this catalyst, acridine catalyst. The red line represents the yield of minor product isolated using this particular catalyst. Please pay attention here and see, it's all flat, unbelievably flat. So therefore, compared to this, the acridine based palladium catalyst seems to be the best catalyst. We have isolated the selective product, and therefore I can clearly tell you that it is possible to isolate only zatine in the presence of methanol and triethylsilane, okay, to isolate the selectively reduced product. Point number 1. You don't need, therefore, the toxic, the most dangerous hydrogen gas for this particular reaction. Point number 2. You don't need the corrosive substances like a formic acid or triethylamine to do this particular process. Point number 4. Then the question comes, what is the role of acridine then? See, it is not coordinating directly to palladium, then why we should have acridine? If you look at the mechanism, you will understand. I will not go in detail about this particular mechanistic aspect, but what I would like to highlight here is this. So what you see here is a transition state where the palladium in principle should exist and satisfy the 18 electron rule to abstract protons from methanol and hydride ions from triethylsilane. This is actually a key step of this particular catalytic process. So therefore, in this key transition state, the acridine in principle should come and support the palladium to facilitate this particular process to form the product. Okay, therefore, presence of acridine is very much essential. Now the question comes, fine, same ligand was used as a medicine, and the same ligand I used it as a ligand. Medicine I used it as a ligand and produced the selective catalyst for semi-reduction of alkyne. How do I convert the ligand into light-emitting material? The answer is following. So as I said, we can nicely pull out the acidic proton and generate a carbene, can become a CNC pincer type of ligand. And so you can actually use this as a ligand and form a nice organometallic compound, and the chromophore such as acridine can certainly help in producing selective emission for the material. Now that is good when you work, for example, with gold. Gold itself is emissive or rare earth metal. Most of the rare earth metals, gold, are luminescent. Now but how about a silver, for example? Silver is not like a gold, okay, light sensitive, very difficult to work with the silver. And therefore, to demonstrate this particular application, what we did, we picked up a silver metal and treated with this ligand and isolated the silver carbene complex. Now the question comes, what is that emission and where you wanted to get the emission? Where are you focusing? So our focus is to generate a material which can emit only blue light. Then the question comes, why blue? Remember, the blue emission was missing quite some time. So the blue emission was discovered by 3 great scientists in the world and received a Nobel Prize in 2014 for the discovery of blue LED. The reason behind was the blue LED was discovered and then it was combined with the red and green to generate a white LED. Why it is so important? Remember, by combining green, red, blue, one can generate a white. So direct white light emitting materials are very rare and very expensive, and therefore even today we all work towards producing direct white emitting material. At least, if not, at least the material should emit blue. This particular work was appreciated for the following reason. See, after we discovered white LED, right, and we use extensively the white LED based materials for domestic applications or day-to-day applications. And this particular white light emitting material can consume a very less power compared to the normal light or any appliance which works with the help of normal light. So how much it can decrease? It can decrease roughly about a 40% of energy consumption of the world, okay, which is actually 1/4 of the world power consumption, which is actually a important contribution to human life. Therefore, this was appreciated very much and awarded Nobel Prize in 2014. Remember, today's LED works with very limited numbers of colors, okay, and they basically work with a complicated algorithm to mix them up and give you different colors on your display, right? Therefore, LED has a own space in the material research area and has a tremendous potential too. By keeping this in mind, what we did, we took this drug molecule and treated with the silver oxide in acetonitrile 24 hours, 45 degrees to isolate the silver acridine carbene complex. So this is the crystal structure of silver complex. It's a beautiful molecule. As you can see here, the acridine is located about 112 degrees towards a silver plane, silver carbene plane. It's in a absolute chair shape, right? Chair shape. It's in a chair shape. No direct relationship between acridine, nitrogen, and gold. Silver. Now the question again comes: then how it will contribute to the emission property of the complex? Because there's no real conjugation between acridine and metal center or carbene. So therefore, I'll give you an answer in the following slide. But when we looked at the emission property of this particular material, it's very interesting. It emits at a deep blue zone. Okay, it emits at a deep blue zone. Very interesting molecule. Remember, the silver-based blue emitting materials are absolutely rare. You will not find any silver blue emitting silver material, and that should be stable, by the way. And the other parameters are quite impressive. And the important point I would like to highlight here is following. This particular material, if you see, emits at 426 nanometer, and it has got a two different excitation point. You can also excite this molecule at 270 nanometer or 358 nanometer. Doesn't matter where you excite, but ultimately what you get is a 426 nanometer emission. That's very interesting. So now you need an answer. Why, how this particular emission occurs, and what is the role of acridine in this molecule? Right. Therefore, to understand this, we did a theoretical calculation, DFT and TD-DFT calculation, and we found that through space, in principle, the acridine interacts with the gold carbene centers. So therefore, the emission output is truly because of the contribution of acridine silver NHC. Okay, acridine silver NHC. So the transition takes place from LUMO of acridine, emission comes from LUMO of acridine to HOMO of acridine silver NHC. So therefore you see one single emission. Okay, therefore you see one single emission. So with this, time has come to conclude nearly my talk. Then we'll have a discussion. I've taken exactly 1 hour to complete my talk now. As I said, we have prepared the acridine N-tetracyclic carbene derivative or N-tetracyclic molecules, and then isolated this molecule and used it as a drug for Alzheimer's studies. It shows a very good Alzheimer activity, and it can fight against Alzheimer disease. Certainly, it shows a promising future in Alzheimer research. And second, we used this as a ligand and produced the palladium-2 based catalyst for selective reduction of alkyne into alkene. And we used this particular drug as a ligand also to make silver carbene complex, which emits at 426, that is actually the deep blue zone, emits at 426 nanometer. Even if you excite this particular molecule in 2 different wavelengths. Right. With this, I thank you all for your kind attention. I will be very happy to take a few questions in case if you have. Thank you very much. Thank you.
Thank you, Professor, for your excellent talk on N-heterocyclic acridine-based drug. and as a catalyst, how it can be a material. Now the session is open for discussions. Friends, you can feel free to ask your doubt, clarifications to Professor.
So are they using a chat box? I should look at the chat box.
Sir, there is no question in chat box.
Oh, I see. I see. No problem, ma'am. Thank you very much. Oh,
Sir, this is Murisa Pandian. Thank you, sir, for nice
Pandian?
presentation. I
yes.
have small doubt.
Murugesh
Yeah.
Pandian,
Yeah,
very
yeah.
well known. Happy
Which
New
salt
Year.
we use for palladium acetate or palladium bromide?
We used a palladium acetate.
Then you convert to the palladium bromide.
Yeah, so
Can I
what
use palladium bromide? No?
it takes away the bromide from ligand and forms
Okay,
a
sir.
palladium bromide.
Oh, okay. So from the ligand precursor, the bromine is coming.
Yes, absolutely right.
Yeah. Okay. Thank you, sir. Thank you.
Thank you very much, Dr. Murugesh Pandian. I wish you a happy new year.
Thank you, sir.
Thank you. So Subhashini has posted saying that useful and informative lecture. Thank you, Subhashini.
Professor, I have
Yes.
small clarification.
Yes, Dr. Prabhakaran, please go ahead.
With the same ligand, which
Yes.
form 3 coordinated compound with silver, as well as it forms 4 coordinated compound with palladium.
Yes. 2 coordination with silver.
Silver.
Yeah. And 4 coordination with the palladium. Yes.
Palladium.
Yes.
Still, silver having empty room for interaction.
Oh, yeah. Actually, the silver love to silver and gold. Basically, if you look at the coinage metal,
Okay.
so the silver love to be in a 2 coordinated stage. It's a silver, gold, and etc. So when you go down, they love even copper also. In most of the cases, yes. But when you move down from copper, silver, gold, and they allow to be in a two coordinated stage. So naturally, in this case, silver lies to be 2. But palladium, if you look at the palladium, the common coordination number of palladium is 4. So they allow to be in a 4 square planar geometrical form.
Yes. Okay, sir.
Thank you very much, Dr.
Thank you, sir. Thank you, sir.
Vinaya Murthy has posted saying that highly informative and interesting lecture, sir. Thank you, Vinaya Murthy. Right. So, yeah.
Now I request Dr. Murugesh Pandian to propose vote of thanks, please.
Yeah, right. Thank you very much.
Good afternoon to all. It's my pleasure to give vote of thanks for this talk. First, I would like to thank Professor Prabhashankar for giving this nice presentation. And he introduced us how the Alzheimer's disease, how we can prevent the Alzheimer's disease by using the impact of chemistry. Okay, so how we can develop a drug for the Alzheimer's disease, and how then the drug can be, how we can convert the drug to the ligand for a coordinate chemistry as well as catalysis, then how it can convert to the light emitting materials. Okay, thank you, sir, for very nice and informative lecture, and it's really nice. Thank you, sir. Thank you.
Thank you very much, Murugesh Pandian. I'm very kind of you. And so I must also be thankful to Dr. Prabhakaran and the whole department for considering me and to deliver my talk in your conference. I'm so kind of you and wish you very happy new year once again. So I'll hope we will meet personally in this year. Yeah, so last year somehow we couldn't do it, but I hope we will meet personally and will conduct many such meetings in your department. I'm looking.
Very kind of you, sir. Thank you very much. Definitely, sir.
Yeah, sure, sir. We'll meet in person. Sure, sir. Thank you, sir.
Thank you. Thanks a lot. Thank you. Also, special thanks to Suresh for keep communicating and updating all the informations. Suresh,
Thank you, sir.
the feedback link. Yeah. Thank you very much.
Thank you, sir. Thank you very much. Thank you. Thank you. Thank you.
Thank you, sir.
Thanks a lot. And see you all. Thank you. Thank you. Thank you all. Bye-bye.
Sir, bye, sir. Bye, sir.
Bye, bye.
Thank you, sir.